Good morning, ladies and gentlemen. Today I'll be covering a topic from the radio navigational aids from basic radar principle and on which I'll be concentrating on primary radars today. I request you to watch till the end of this video because during this lecture I'll be covering some of the probable exam questions. I'll be covering this topic under the following headings like the basic principles, the computation of maximum and the minimum radar range, the application of radars and the advantage of primary radars. The name radar comes from these four words. There is radio, detection and ranging. The RA from the radio has been taken out, D from detection, A from and R from ranging, which combines together form the word radar. The radars use a frequency band of ultra high frequency and super high frequency. On the ultra high frequency, the frequency ranges from 300 to 3000 megahertz and the wavelength ranges from 10 centimeters to 100 centimeters, and they are typically used for the long range radars. Whereas the super high frequency band, the frequency starts at about 3 to 30 gigahertz and the wavelength will be from 1 centimeter to 10 centimeters, and they are typically used in radio altimeters, airborne weather radar and for the short range radar. So why do we have to use this frequency? By using this frequency, that is VHF and above, the external noise is being reduced and also the ionospheric scatter is being reduced. At these frequencies, narrow beams can be created for a better resolution. We will talk about the resolution at the later part of the class, and this also can produce a very short wavelength. The shorter pulses can also be produced with a shorter wavelength. The efficiency of reflection, that is from the target object, depends upon the size of the object in relation to the wavelength. A shorter wavelength, the signal will be reflected more efficiently by the reflecting object. The different types of radar which we use in aviation are primary radars. A primary radar transmits a pulse of radio energy towards a target. These pulses are then reflected from the target. These reflected waves are received by the receiver to compute range and the bearing of the target. Whereas a secondary radar transmits pulses, which we call it as interrogation pulses. So that means the transmitter interrogates on one frequency. This interrogator may be a ground station or an aircraft to a target, which again may be a ground station or an aircraft. The target receives the frequency and it transmits or responds on a different frequency. This responded signal is used to compute the range, bearing and the other information, additional information, which we will talk about when we talk about the secondary radar like the SSR and the ADSB. The station which interrogates is known as the interrogator and the target is known as the transponder. Further proceeding ahead, these radars may be again classified under the pulse radar. These radars transmit a burst of a signal for a very short period of time known as a pulse. So this is for a short period of time. Follow my mouse please. Okay, and they have to wait for this pulse to return after reflecting from the target. Okay, this reflected signal is used to compute the range as well as the bearing of the target. Whereas the continuous wave radar transmit a progressively changing wave which are modulated modulated, and this modulation depth is known to the transmitter, and the reflected signal is compared, okay, with that frequency which is transmitting at that moment of the time, and the change in the modulation is what is used to resolve the range and the direction of the target. We will talk about the continuous wave radar in some of the class in the future. So when we talk about the pulse radar, as we have mentioned earlier, it transmits a burst of pulses like the one which is shown by my mouse. Okay, diagrammatically it can be represented down below like this. The duration for which the waves are transmitted or the bursts of signal are transmitted is known as the pulse rate. So the pulse rate is the length of this particular burst of signal which are transmitted, which are where the mouse is hovering. And whereas after having transmitted the first wave, after some time the second burst will be transmitted. The time interval between two such bursts or the pulses is known as the PRI. So the PRI or the pulse recurrence interval is the time interval between two pulses. It is also known as the pulse recurrence period. Here in this example, 2 microseconds is the pulse width and the 6 microseconds is the pulse recurrence interval. This pulse recurrence interval is measured from the leading edge of the first pulse to the leading edge of the second or the subsequent pulse. Then we have got the pulse recurring frequency. As we have seen that the time between the two pulses. So how many such pulses are transmitted in a second is known as the pulse recurring frequency. So pulse recurring frequency is the number of pulses transmitted in 1 second, which is also known as the pulse recurring rate or PRR. So if we try to correlate between the PRR or the pulse recurring frequency and the PRI, they will be reciprocal to each other. So therefore, if the PRF is 500 pulse per second, what will be the PRI? So the PRI will be 1 upon PRF. So therefore 1 upon 500 seconds, which when converted to microseconds will be 2000 microseconds. So how do we measure the distance of the target? That is, in this case, the distance of the aircraft. The distance measurement of a primary radar, pulse radar, is done by the range by echo principle. So the wave will be transmitted from the transmitter to the aircraft, and that has to come back from the aircraft to the transmitter after having reflected from the aircraft. So the total time of travel from the antenna to the aircraft and from the aircraft to the antenna is measured. So if we have got the time, by the formula distance is equal to velocity into time, we can compute the distance. So here in this case, the velocity will be the velocity of the electromagnetic wave, that is the speed of the EMF wave, and the time taken is to and fro. So therefore the distance traveled will be half of this, because the wave has traveled twice the distance. So if the pulse takes 2000 microseconds to come back, what is the range of the target? With the same formula, distance is equal to velocity of the electromagnetic wave into time taken to travel to the aircraft and come back from the aircraft. So the speed of the sound in meters per second is 3 into 10 to the power 8 meters per second, multiplied by the time taken in microsecond, which when converted to seconds. Okay, so since 2000 microseconds will be 2000 upon 1 million, so the figure comes from here, divided by 2, because the wave has traveled twice the distance. So therefore the range or the distance of the target from this antenna will be 300,000 meters, which when converted to kilometers will be 300 kilometers, which divided by 1.852 will give me the distance in nautical mile, which is 162 nautical miles. Similarly, if the question is asked to compute the distance in terms of nautical miles, we can use the same formula, that is distance is equal to speed into time. The speed here is 162,000 nautical miles per second is the speed of the light or speed of the electromagnetic wave, multiplied by 2000 microseconds, which is converted to seconds will be divided by 1 million, okay, divided by 2, which is 162 nautical miles, which when converted back to nautical miles, kilometers will be 300 kilometers. So this is how the radar measures the distance of the aircraft by the echo principle. So how much can be the maximum theoretical range of the primary radar? So since the maximum range will be a function of the time between the conjugative pulses, which is known as the PRI. Basically, before I start transmitting the signal, okay, I have to receive the reflected signal from the aircraft. Till the time I receive the reflected from this aircraft, I cannot transmit. So therefore, this gap, that is the PRI, the pulse interval, okay, will define the maximum range. Within this period of time, the wave has to go towards the aircraft and come back from that aircraft or the target back to the antenna. So therefore, the distance which when converted in terms of the time of travel, which is decided by the PRI, will be the maximum distance of or range of a radar. So as the wave is to travel to and fro within 2 consecutive pulses, the maximum theoretical range will be PRI upon 2, or in other words, okay, the maximum range will be a function of the PRF, since PRF is equal to 1 upon PRI. So let us calculate the maximum range of a radar. Calculate the maximum range of a radar with a PRF of 400 pulse per second. So PRF is equal to 400 pulse per second, which when converted into PRI will be 1 upon 400, which will be decimal 0025 seconds. So therefore, the range will be 3 into 10 to the power 8 meters per second into the number of seconds, that is decimal 0025 upon 2, which is 375,000, that is 375,000 meters, which when converted to kilometers gives me 375 kilometers. So therefore, a radar which has got a pulse recurring frequency of 400 pulse per second will give me a maximum range of theoretical range of 375 kilometers, which when converted into nautical miles will be 202.5 nautical miles. So apart from that pulse PRI, the maximum range of the primary radar will also depend upon the power of transmission. A radar signal attenuates with increasing distance from the transmitter. If the range must be increased by twice, then the power has to be increased by 16 times. It also depends upon the characteristics of the reflecting object, like the size of the target, the aspect ratio of the target, and the type of material, which is the target material. Also depends upon the height of the antenna and the height of the aircraft. The formula to calculate the maximum range is range will be equal to height of the transmitter multiplied by 1.25 plus height of the receiver multiplied by 1.25. It will also depend upon the atmospheric condition. Inversion. In case of an inversion, there is increase of temperature with the increase in height. Normally, with the increase in height, the temperature drops down. But in case of an inversion, there will be an increase in temperature with the increase in height, and also decrease of humidity with the increase in height may cause a phenomena which is known as the super refraction. In which case, the wave will try to bend towards the surface of the earth, which increases the range beyond the line of sight. On the other hand, the subrefraction, which is opposite of what we have discussed, will reduce the range of the radar. If there is a presence of the rain in the atmosphere, okay, a wavelength of between 4 to 10 centimeters are absorbed or scattered by the raindrops. So therefore, you will have a weak return of a ground radar if you use the wavelength of 4 to 10 centimeters. So therefore, a long range radar, okay, will normally have a wavelength which is more than 10 centimeters, and the weather radar, that is the airborne weather radar, will use a frequency which is around 3 centimeters, and surface movement radars will use a wavelength which is of 1.75 to 2 centimeters. And it will also depend upon the restoration time, which is a delay which is inside the system. Okay. So how do we determine the minimum range of a pulse radar? Is we have seen that the primary radar uses only single antenna, because of which this particular antenna cannot transmit while it is receiving, or it cannot receive while it is transmitting. So the transmitter cannot receive when it is transmitting, and vice versa. Therefore, the minimum range will be restricted by the duration for which the pulse is transmitting, which is nothing but the pulse rate. Therefore, the minimum range of a radar will be the distance corresponding to the pulse weight. So let's have a look with a numerical. That is, calculate the minimum range of a radar with a pulse weight of 2 microseconds. So here in this case, 2 microseconds is the pulse weight. The minimum range which can travel is 3 into 10 to the power 8 meters per second, multiplied by 2 microseconds, which when converted will be divided by 1 million divided by 2, which gives me 300 meters. So if you have a radar with a pulse weight of 2 microseconds, the minimum distance or the range is 300 meters. So now coming back to the basic principle, we have talked about how do we determine the distance or the range of the radar. Now how the direction is being determined. The direction determination is, the principle is known as the bearing by search principle. Now this beam is being continuously rotating from clockwise. So whenever these beams falls onto the aircraft, this will be reflected back. The direction from where this reflection comes back is indicated as a dot onto the scope of the radar. So this is how the primary radar finds out the direction of the target. So now these targets which have been detected by this radar, how they are shown onto the target, and what will be the resolution. That means that the resolution means the size of the target which is indicated onto the scope. The size of the target which is indicated on the scope will depend upon the pulse width and the beam width. Now let's have a look at the pulse width. Now the pulse is traveling, hits the target, and comes back. So while he is traveling, once again I will show you the animation. While he is traveling, half way through it has the leading edge of the pulse will start transmitting back. Till the time the transmission occurs, till the time the trailing edge of that pulse will transmit. So there will be half of the pulse weight additional will be painted for a point target. So therefore the range resolution, okay, will be decided by the half the pulse weight, okay, for a point target. So for a pulse weight of 1 microseconds, the point target will be painted for 300 upon 2, because 1 microseconds length which when converted into distance will be 300 meters divided by 2, okay, so with 150 meters. A point target, okay, will be painted on this particular radar as a 150 meters long target. As far as the azimuth is concerned, okay, let us have a look. This is the point target. This point target will start painting, okay, when if the direction of rotation of this antenna is clockwise, it will start painting since from the time the leading edge of this beam starts hitting the target till the time the trailing edge of this beam hits the target. So therefore, the bearing resolution will be a function of the beam width of the signal. So therefore, if you have a radar whose beam width is 2 degrees and the distance of the target is, let us say, 60 nautical mile, okay, by applying 1 in 60 rule, okay, that is 2 degrees 60 nautical miles, this point target will be painted on a radar scope, okay, for a bearing or azimuth range of 2 nautical miles. So in order to improve this, okay, for the range resolution, okay, we must have a shorter beam width. As far as the resolution, that in terms of azimuth is concerned, we must have a narrow beam width. How do we achieve this? Okay, the narrow beam width can be achieved by increasing the size of the antenna. The application of this primary radar, which we have talked about, is on a ground radar, airborne weather radar in order to detect the weather, secondary surveillance radar. We will talk about the secondary surveillance radar and in a subsequent classes. It can also be used for radio altimeter or a radar altimeter, and it is used for the distance measuring equipment, which we call it as a DAV. The advantage of using the primary radar is that it is self-sufficient. There is no cooperation required from the target. Okay. The peak power can be increased because the actual time of transmission is for a very, very short time. Okay, as we see that it is transmitted as a pulse. Only one antenna is used for both transmission and reception, and if it is on for a ground installation, the beam width can be further narrowed down by using a very large size area. Some of the questions we can expect is that what is the factor which determines the maximum range of a radar? If the PRF of a primary radar is 600 pulse per second, find out the maximum range of the radar. The time between the transmission of a pulse and the reception of an echo from a target is 1800 microseconds. Then what is the range of the target? A radar is required to have a maximum range of 200 kilometers. What will be the maximum PRF? What determines the minimum detection range of a radar? So if you want, you can solve this numerical and send it on the comment box so that we can cross-check it. At the end, I request all of you to kindly press the subscribe button and also to press the bell icon so that any new video which is released by me will be informed to you. And if you feel that it is worth, you can share it with your fellow aviators. I thank you once again for watching this video till the end. Have a nice day.